The story we've always been told about how our planet was born, it's a lie. We pictured a simple, slow start, a fiery ball that just patiently cooled down over billions of years. We thought we knew, but it turns out we were wrong. What if the rocks right under our feet hold the secret to a violent, chaotic beginning that changes everything we thought we knew about the world? A shocking discovery hidden in Earth's oldest bits has pointed to a fiery, brutal origin we never imagined. This isn't just a new chapter in a geology textbook. It completely changes how we think about planets becoming home. Our world's chemical fingerprint was forged in fire billions of years earlier than we ever thought possible, connecting us to the most extreme moments of our planet's birth. For decades, the story of Earth's birth was simple and slow. It's what you learned in school. A hot, hostile planet was born, slowly and methodically cooling over geological ages. The main idea was that the early Earth was a pretty uniform melted ball. Once it cooled, it was thought to have formed a simple, basic crust. This first skin was believed to be dark, heavy, and made of basalt, much like the rocks on today's ocean floor. Geologists called it a stagnant lid, a mostly unbroken shell that covered the entire planet. According to this long-held theory, the world we know today, with its towering, lighter granite continents, was a much, much later development. Geologists believed that creating continents needed a powerful engine, plate tectonics. The theory said that for continents to form, huge plates of the crust had to start moving, crashing into each other, and diving beneath one another in a process called subduction. In these subduction zones, these recycling plants of the planet, is where the real magic was supposed to happen. As one plate plunged into the mantle, intense heat and pressure melted the rock, separating and transforming it. This created new, lighter magmas that rose, erupted, and built the foundations of continents. A key piece of evidence for this was a distinct chemical fingerprint in continental rocks, a noticeable lack of an element called niobium. Scientists assumed that this niobium anomaly was a clear sign of subduction. The logic was, if we could find the oldest rocks with this feature, we'd know when plate tectonics began, and with it, the birth of the first true continents. The model was elegant and made sense. It painted a picture of a planet that perhaps had to wait a billion years after its formation for its tectonic engine to finally kick into gear. The Hadean Eon, Earth's first 500 million years, was known as a period of early simplicity, a planet with a basic crust just waiting for the real show to begin. But science is a story that's always being rewritten. And as new tools allowed us to peek deeper into the past, clues started popping up that just didn't fit the picture. The whispers from ancient minerals suggested that the story of our planet's first continents wasn't about slow development. It was about sudden, violent creation. To understand this new discovery, we need to go way, way back. Before Earth, before the Sun, there was just a huge, swirling, cold cloud of gas and dust floating in the Milky Way. This was our solar nebula. For millions of years, it was just one of many clouds in our galaxy. But then something happened. Maybe a nearby supernova, the last gasp of a dying star, sent a shockwave that squeezed the cloud. Or maybe it was just the slow pull of its own gravity. Whatever started it, it began to shrink. In the center of this shrinking cloud, material got denser and hotter until the pressure kicked off nuclear fusion. Our sun was born. When it first fired up, it blew away most of the gas around it, revealing a flat, spinning disk of leftover dust and rock. This was the protoplanetary disk, the space nursery where all the planets grew up. And this disk wasn't just dust. We've seen in other places where stars are forming that these clouds are full of complex organic molecules. These are the basic parts of life. Carbon-based compounds needed for everything from amino acids to sugars. The basic ingredients for life weren't added to Earth later. They were mixed into the cosmic dust from the very beginning. In this spinning disk, a delicate dance began. Tiny dust grains started to stick together, first because of electrostatic charge, like dust bunnies under your bed. The grains grew into clumps, the clumps into pebbles, and the pebbles into rocks. It was a cosmic snowball effect called accretion. As these objects got bigger, their gravity started pulling in even more material. The protoplanetary disk was a messy demolition derby with millions of small bodies called planetesimals crashing into each other. Some collisions smashed these baby worlds back into dust, but others created new things, merging two bodies together. In the hotter inner part of the solar system, only materials that could withstand high heat could survive. metals like iron and nickel, and silicate minerals. This violent process went on for millions of years. Planetesimals grew into protoplanets, reaching the size of our moon or Mars. One of these, in just the right spot, was well on its way to becoming Earth. But its birth was far from over. The most intense days were still to come. The birth of Earth wasn't a gentle event, it was a cosmic bombardment that lasted for 100 million years. The protoplanet that would become our world grew through a relentless series of catastrophic collisions. Each impact delivered more mass and unimaginable amounts of energy. This was the Hadean Eon, named after Hades, the Greek underworld, and for good reason. Imagine a planet made not of rock and water, but of fire. The energy from the constant impacts was so immense that the entire surface was a global ocean of molten rock, a magma ocean thousands of miles deep. The surface would have glowed a menacing red-orange, bubbling and churning like a cosmic cauldron. There was no solid ground, just a turbulent sea of liquid rock under a suffocating sky of vaporized rock and poisonous gases. Any early atmosphere was likely blasted away by the next giant impact, only to be slowly replaced by gases escaping from the molten interior. For decades, scientists thought this magma ocean slowly solidified from the bottom up. But new research is challenging even that idea. It turns out early Earth was far more chaotic. Much of the crystals that make up the mantle actually formed near the surface at lower pressures before sinking down or being dragged along by the violent swirling convection of the magma ocean. It wasn't a simple layering, but a turbulent mixing bowl. Crystals formed in the slightly cooler upper layers only to be pulled back into the inferno. As this Hadean chaos began to subside and the bombardment lessened, the planet could finally cool. Heat radiated out into space. A thin, fragile crust of solid rock would try to form on the surface only to be shattered by the next impact or dragged back down. But with each passing million years, the cooling continued. Larger, more stable pieces of crust began to form. This was the birth of Earth's primordial crust. And here, in this ancient skin, forged in the dying embers of the magma ocean, lay hidden the first great secret of our planet's birth, waiting 4.5 billion years to be found. As the young Earth swirled as a magma ocean, another key process was happening: differentiation. In its molten state, the planet was a soup of mixed elements. But just like oil and water, elements started to separate based on their density. The heaviest ones, mainly iron and nickel, began a slow but unstoppable journey towards the planet's center. This process, called core formation, was the most important event in Earth's early history. Droplets of molten iron, much denser than the silicate magma around them, trickled downwards, joining up into bigger blobs. They sank thousands of kilometers through the liquid rock, eventually gathering at the very bottom of the planet to form a dense metallic core. This created Earth's layered structure: a core, a mantle, and a crust. And the movement within that liquid outer core would one day create Earth's magnetic field, the protective shield that allows life to thrive on the surface. But core formation did more than that. It fundamentally changed the chemical makeup of the rest of the planet. As the iron sank, it took with it what we call iron-loving elements. This is where our story takes a turn, and where that specific element, niobium, comes back into play. Niobium is normally lithophile, meaning it prefers to stay in the rocky mantle and crust. The old theory said niobium should have stayed in the mantle. But groundbreaking new research found that the Hadean Eon had a very different chemical environment. It was highly reducing, meaning there was very little oxygen available. And it turns out, under these specific conditions, niobium changes its personality. It becomes siderophile. It starts to like iron. This is the eureka moment. As the iron droplets plunged through the magma ocean to form the core, they snatched up a huge portion of the mantle's niobium and dragged it downwards. This left the remaining mantle, the material from which the future crust was made, permanently poor in niobium. The infamous niobium anomaly that chemical fingerprint geologists had attributed to plate tectonics for so long could have been created billions of years earlier. It wasn't necessarily a sign of crustal recycling. It was an ancient mark, a birthmark from the day Earth's core was formed. The evidence pointed to an event that happened at the very beginning. The young Earth, still separating its core and mantle, wasn't alone. It shared its orbit with other large protoplanets. One of these was a Mars-sized body that scientists named Theia. For a while, Earth and Theia probably had a stable relationship, but stability in the early solar system was a fragile thing. Their dance was destined to end in the most violent collision in our planet's history. About 30 to 50 million years after the solar system formed, Theia was hurtling towards Earth on a catastrophic collision course. It wasn't a direct hit, but a glancing blow with almost unbelievable force. The energy released was incredible, instantly vaporizing Theia and huge parts of Earth's mantle, blasting a colossal cloud of molten rock and gas into space. This was a planet-forming event. Earth itself was knocked off its axis, giving us the tilt that causes our seasons. Theia's dense metallic core likely plunged through Earth's mantle to merge with our own, but that's not the whole story. Deep within Earth's mantle today are two continent-sized blobs of chemically distinct material. A fascinating new theory suggests these blobs are actually the dense, iron-rich remnants of Theia's mantle, which sank and have remained there for 4.5 billion years. If this is true, we live on a planet that still carries the buried remains of another world in its heart. Meanwhile, the cloud of debris blasted into space didn't escape Earth's gravity. It formed a hot, glowing ring of rock around our planet. Within this ring, accretion began anew. In a surprisingly short time, perhaps just millennia, these clumps merged into a single large body. The Moon was born. This giant impact hypothesis explains why the Moon is so big compared to Earth, why it has a tiny iron core, and why its chemical makeup is so similar to our mantle. The Moon, in a very real sense, is Earth's child, born from the most violent event in our planet's history. This cataclysm set the stage for the formation of the planet's first permanent crust. The stage was set, and the true, surprising nature of Earth's first skin would soon be revealed. For billions of years, we thought the story of the Hadean Eon was completely lost, erased by our planet's constant changes. Rocks from this super-old time are incredibly hard to find, but geologists found a clue: tiny super-tough crystals called zircons. These zircons, found in much younger rocks in places like Jack Hills, Australia, are like microscopic time capsules. Scientists have found zircons that are up to 4.4 billion years old. That means they formed when Earth was just a baby planet. These are the oldest known pieces of our world. As our research tools got better, scientists could look for even smaller clues in these ancient messages, and what they found was very surprising. The old story just didn't make sense anymore. The big breakthrough came from mixing new computer models with a fresh look at the evidence. A group of scientists decided to question the old idea about plate tectonics. What if that special chemical signal, the niobium anomaly, wasn't created when plates moved under each other, but was there from the very beginning? They used computer simulations to model what the early Earth was like when its core formed. Their discoveries were a huge breakthrough. They showed that any crust that formed from the mantle after the core formed would naturally have low niobium levels. This chemical fingerprint wasn't made by plate tectonics. It was something the planet inherited from its very first moments. This meant that the protocrust, Earth's very first stable outer layer, had surprisingly similar chemical stuff to today's continental crust. This completely changed how we thought about things. Earth's first stable land wasn't just a simple, dark, rocky shell. It was much more advanced, similar to the floating, silica-rich continents we have today. Our planet's very first solid ground might have already contained the basic parts that make up continents. So how did this happen without modern plate tectonics? The new model says it was a messy process. As the ocean of melted rock cooled, a protocrust formed, but it was broken and cracked. It would have been constantly hit by meteorites during what some call the late heavy bombardment. This chaos would have changed the protocrust. In some places, the pieces got thicker, becoming the first cores of continents. In the cracks between them, melted rock from deep inside rose up, creating crust like our modern ocean floors. So, instead of a smooth planet, the Hadean Earth could have quickly developed two kinds of crust: thick, floating, continent-like crust, and thinner, heavier, ocean-like crust. This discovery tells us that continents started forming much earlier than we thought, maybe in the first 100 to 200 million years of Earth's life, not a billion years later. Plate tectonics later became the main force for shaping and recycling continents, but it wasn't how they started. The foundations were laid much, much earlier, built into our planet's chemistry from the very beginning. Just as Earth was forming its first crust, the solar system had one last violent event in store. From about 4.1 billion to 3.8 billion years ago, The inner planets were hit by tons of asteroids and comets. This time is called the Late Heavy Bombardment, though some scientists now wonder if this sudden increase in impacts was really that sudden. We can see the proof on the moon's surface. Its big dark areas are actually huge impact craters. Samples from the Apollo missions showed that many of these formed in a pretty short amount of time. On Earth, the direct proof is gone, but the effects would have been terrible. The sky would have fallen with fire. Asteroids, hundreds of miles wide, hitting Earth would have punched holes in the new crust, making temporary lakes of melted rock. But this bombardment wasn't just about destruction, it was also a kind of delivery service. Early Earth, which formed in the hot inner solar system, was probably a dry, rocky planet. So where did our oceans come from? The answer, people say, fell from the sky. Asteroids and comets from this time weren't just simple rocks. They were messengers from the colder, outer solar system, and they brought something very important with them: water. Comets are sometimes called dirty snowballs because they have a lot of ice water, and some asteroids can also hide a surprising amount of water in their rocks. For hundreds of millions of years, these cosmic delivery trucks arrived, dumping their water onto the hot, empty surface. It's amazing to think almost every drop of water in our oceans might have come from the cold, deep space, brought here during this time of intense cosmic violence. The chemical makeup of Earth's water even matches the water found in certain types of asteroids, which suggests they were the main source. At the same time, volcanoes were spitting out huge amounts of water vapor that was trapped inside Earth. With this, they brought the most important thing for the world that was to come. As the heavy bombardment finally calmed down about 3.8 billion years ago, Earth entered a period of relative peace. Water, both from space and released by volcanoes, existed as a thick, dense blanket of vapor in the atmosphere. The planet's surface was still too hot for liquid water, but as the planet kept cooling, a turning point arrived. The atmosphere, full of water vapor, started to condense. The first clouds formed, and then it started to rain. This wasn't just a shower. This was a planet-wide flood that might have lasted for millions of years. Hot water poured from the sky, hit the hot crust, boiled back into steam, and fell again in a never-ending cycle. Slowly, as the surface cooled below the boiling point, the rain started to collect. It filled the huge basins between the early continents and the craters left by the bombardment. The first oceans were born. They weren't blue and salty like they are today. They were likely acidic and full of dissolved iron, which gave them a cloudy olive-green color under a thick sky full of CO2 and nitrogen. That early atmosphere was totally alien. It had almost no free oxygen and might have been a dozen times thicker than the air we breathe today, made mostly of nitrogen, carbon dioxide, methane, and ammonia. This thick blanket of CO2 created an intense greenhouse effect, keeping the planet warm even though the young sun was much dimmer, a mystery known as the faint young sun paradox. The formation of the oceans started to change the atmosphere. Carbon dioxide began to dissolve into the seawater, where it reacted with rocks on the seafloor. This slowly started to reduce the amount of CO2 in the air, kicking off a geological carbon cycle that still helps regulate our planet's climate today. The world had now fundamentally changed. It was an aquatic world with the key ingredients for life: liquid water, energy, and organic building blocks. The stage was set. Our journey to understand Earth's birth doesn't end here. To truly grasp how special our planet is, we need to look out into space. With thousands of exoplanets now discovered, we see that the processes that shaped our world are part of a larger cosmic story. Systems like WASP-132, for example, show us a giant planet orbiting incredibly close to its star, with smaller rocky planets nearby. This challenges our classic models and suggests that complex planetary systems can form in many chaotic ways. Our solar system is just one possible outcome of the cosmic roll of the dice. Closer to home, there's Mars. Our rovers have shown us a world that might have started on a similar path. Evidence of ancient river deltas and lake beds tells us that Mars once had liquid water on its surface, but at some point the paths of the two planets diverged. Mars, being smaller, cooled down faster. Its internal dynamo shut off, and it lost its magnetic field. The solar wind then stripped away its atmosphere, and its water either evaporated or froze. Mars is a stark reminder of how fragile a habitable world can be. Earth's continued success is thanks to its size, its active geology, and a delicate long-term climate balance. These cosmic comparisons give us perspective. They show us that a planet like Earth isn't a given. It's the result of a specific, chaotic sequence of events. And the discovery that the chemical origin of our continental crust lies in Earth's very first moments adds another fascinating layer to the picture. Perhaps this niobium fingerprint is a key indicator to look for in distant rocky worlds, a sign that a planet had the right starting conditions to evolve into a world we might one day call home. Once the continents were in place, the oceans were formed, and the air had settled down, the final part of Earth's creation could begin. By then, the planet was like a giant science lab. In the sunny, shallow waters, in the bubbling, hot ocean vents, or in tiny, warm puddles, the change from complex chemicals to simple living things was just starting. All the basic ingredients were there. Organic molecules from comets and space rocks mixed into the oceans, and energy from the sun, plus the planet's own inner heat. We might never know exactly when the first molecule that could copy itself showed up, but it happened about 3.8 billion years ago. Life had begun. At first, it was super simple. Tiny, single-celled creatures just barely getting by in a world without oxygen. For billions of years, these simple microbes were the only rulers of the planet, but they weren't just sitting around. About 2.5 billion years ago, some bacteria learned a cool new trick: photosynthesis. They figured out how to use sunlight for energy, and when they did, they released a byproduct, a harmful, very active gas called oxygen. This great oxidation event was the biggest pollution event in Earth's history. Oxygen was poison to most living things, but for those who adapted to it, it opened up a whole new world. Oxygen cleaned the oceans of dissolved iron and built up in the air, creating the ozone layer. This paved the way for a new kind of life, allowing bigger, more complex life to form. Life didn't just appear on Earth, it grew with the planet, changing the air, the oceans, and the very rock beneath our feet. This incredible story is written in the rocks all around us, and scientists are learning new pages to read every single day. If you find these cosmic mysteries as fascinating as we do, then hit subscribe and ring that notification bell so you don't miss our next journey into the deep past. From a swirling cloud of dust, it became a glowing, broken world, then a global ocean under a toxic sky. Our planet's birth was a story of incredible power and amazing changes. For a long time we thought it happened slowly and simply, but the secrets hidden in Earth's oldest minerals showed us a new truth. Our world was born with a hidden power. The chemical mark of our continents, the very base of our home, wasn't added later. It was a birthmark, formed on the super-hot early Earth, right when our planet's core was made. This discovery changes how we see things. It shows us a planet that was active and complex right from the very start. It connects the ground beneath our feet to the making of the core and that huge event that created our moon. Earth's 4.5 billion year story is one of constant, often wild changes. We're just living through a tiny part of a very long movie. By uncovering these secrets, we not only learn where we came from, but we also get a deeper appreciation for the special and precious world we get to call home. And the story is far from over. The rocks still hold their secrets, just waiting for us to ask the right questions.